Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The tiny world that shouldn't be this complicated. In our solar system, there's a type of object that's incredibly easy to overlook. It doesn't glow. It doesn't explode. It doesn't put on any dramatic show. It just sits quietly between Mars and Jupiter, like background static in a cosmic broadcast. And yet NASA decided it deserved a spacecraft of its own. Not a quick flyby either, an actual long-term mission, looping around it and taking tens of thousands of images. At first, you might think, did NASA just have extra budget lying around? But the more you look at it, the more that idea falls apart. Because maybe the problem wasn't that it was unimportant. Maybe we just misunderstood it from the start. Its name is Ceres, about 940 kilometers across. In the asteroid belt, it's basically a heavyweight champion. But in planetary terms, it doesn't even make the cut for the official roster. And then things get weird. When NASA's Dawn spacecraft got close, it spotted something unexpected: bright white patches scattered across the surface, especially inside a crater. In 2015, when those images came down, the planetary science community basically went quiet for a while, because those spots didn't look normal. Not at all. They were too bright, almost like someone had spilled salt across the surface. Later analysis confirmed it, mostly sodium carbonate and other salts. In simple terms, dried up salt flats. But that immediately raises a bigger question: how do you get salt deposits on a tiny world stuck in the asteroid belt? Because where there's salt, there was almost certainly liquid water. And where there's liquid water, things stop being simple. That's when a more uncomfortable idea appeared. Maybe Ceres wasn't always a dead rock. Maybe it was once a small water-rich world, limited, yes, but internally active enough to matter. And that leads to a bigger problem: have we been underestimating small bodies in general? But before jumping to conclusions, we have to rewind to 1801, because that's when this whole story started to glitch. Back in the late 18th century, astronomers were excited about something called the Titius-Bode rule. It was a neat mathematical idea suggesting that planetary distances from the Sun followed a predictable pattern. And strangely enough, it seemed to work. It even roughly matched Uranus's orbit. That was enough to spark confidence: the universe follows rules, and we can calculate them. So when there was a gap between Mars and Jupiter, scientists assumed something must be missing there. Naturally, a full-scale search began. Not casual observing, systematic sky surveys, scanning section by section like mapping an unknown ocean. Then, on January 1, 1801, Giuseppe Piazzi at the Palermo Observatory noticed something moving. Not a star, it shifted position. Not a comet either, it had no tail. So he tracked it carefully and confirmed it was orbiting the Sun. It was named Ceres. At first, everything seemed fine, even a bit celebratory. But then it disappeared. Not exploded. Not drifted away. Just lost. They couldn't calculate its position anymore. The orbit didn't make sense with the available data. It was like finding something and immediately forgetting where you put it. It sounds absurd now, but at the time, it was a real crisis. Because if you can't predict orbits, then the whole idea of mathematical astronomy starts to wobble. That's when a young mathematician stepped in, Carl Friedrich Gauss. Barely in his 20s, not yet the legend he would become. No new observations. No better telescope. Just incomplete data. And still, he did something almost no one believed was possible: he reconstructed Ceres's orbit mathematically. Not just estimating it, calculating where it would reappear in the sky. And he was right. When astronomers followed his prediction in late 1801 and early 1802, they found Ceres again, almost exactly where it should have been. It was one of those rare moments where mathematics didn't just describe reality, it recovered it. Some would even call it the beginning of modern orbital computation. But that wasn't the end. It was the beginning. Because once Ceres was found again, more objects started showing up in the same region, one after another. Soon the problem changed. If all of these are planets, the solar system's official list becomes unmanageable. So the solution was simple, if a bit brutal: redefine the categories. Ceres was downgraded from possible planet to asteroid number 1. Not because it changed, but because there were too many neighbors. As the saying goes, if everything is special, nothing is. And that's when astronomers realized something deeper. There wasn't a missing planet between Mars and Jupiter. There was a whole belt of material, the asteroid belt. And Ceres wasn't a missing piece. It was just the largest surviving fragment. Or at least, that's what it seemed. Because over time, that fragment started acting less like debris and more like something far more complicated. When Ceres was officially placed back into the celestial catalog, scientists thought the story was basically over. They were wrong. Because instead of settling down, things escalated into something far messier. As the saying goes, you fix one problem, and 3 more show up. And in this case, the solar system's middle region basically turned into a construction site. Starting in 1802, objects just kept appearing in the same zone between Mars and Jupiter. Not 1 or 2 dozens over time. By 1804, Vesta had already been found. In 1807, Juno joined the list. Suddenly, the timeline looked like this: Ceres first, then Vesta, then Juno, and more kept coming. Astronomers started to feel something was off. At first, they thought there was simply a missing planet. But now it looked less like a missing planet, and more like an overcrowded neighborhood nobody had mapped properly. By the mid-19th century, things were out of control. Telescope technology improved, sky surveys expanded, and more objects kept turning up. Eventually, there were dozens. And that created a serious problem. If all of these were called planets, the solar system would become impossible to manage. Even textbooks would fall apart. So scientists did something very practical: they changed the rules. Ceres was quietly reclassified into a new category as asteroid number 1. Not because it changed, but because the population exploded around it. As the saying goes, if everything is important, nothing stands out. But strangely, this downgrade didn't end the story. It created something new: the concept of the asteroid belt. In the mid-1800s, astronomers like Heinrich Olbers proposed a bold idea: these objects weren't randomly scattered. They formed a structured region of debris. Maybe it was material that never formed a planet. Or maybe a planet that started forming and broke apart early on. Modern science leans toward the first idea, but at the time, it was still shocking. Because it meant something very different. Between Mars and Jupiter, there wasn't a missing planet. There never was one. Ceres became the largest surviving piece of that unfinished story. Fast forward to the 20th century, and the solar system finally looked stable. The planet list was settled until 2006. That year, the International Astronomical Union met in Prague. What looked like a routine conference ended up rewriting astronomy textbooks. The question was simple but explosive: is Pluto actually a planet? Pluto had always been a bit of an odd one: tilted orbit, high eccentricity, sometimes even crossing inside Neptune's path. So the IAU defined 3 rules for a planet: orbit the Sun, be round, and clear its orbital neighborhood. Pluto passed the first 2. It failed the third. So it was reclassified as a dwarf planet. Ceres joined the same category. But their stories couldn't be more different. Pluto lost its planetary status. Ceres never really held it in a stable way in the first place. Still, 2006 became a symbolic crossroads: one object losing identity, another finally gaining a defined one. But the real shift didn't happen in 2006. It started with a mission, Dawn spacecraft. Launched after 2007 and fully active by 2015, Dawn had an unusual design: 2 destinations, not one. First Vesta, then Ceres. The goal was simple but deep: is the asteroid belt just rubble, or leftover building material from failed planets? In 2011, Dawn arrived at Vesta. By 2012 it left. Then in March 2015, it entered orbit around Ceres, first time humanity had ever studied a dwarf planet up close. At first glance, nothing special. Gray surface, craters, a quiet, almost boring world. A low-energy moon, basically. until the white spots showed up. Inside a crater, bright patches appeared, so reflective they almost looked artificial, like molten metal splashed onto dark rock. Even from different orbital heights, the brightness stayed consistent. Scientists' first reaction was brutally honest: something about this doesn't add up. So the hypotheses came fast: ice, salt, cryovolcanic residue, volatile deposits. Over time, the answer narrowed: mostly sodium carbonate salts. In other words, dried salt deposits, like ancient salt flats on Earth. But that immediately raised the real question: where did the salt come from? Further analysis suggested something more unsettling: these deposits may be connected to subsurface liquid water activity in the past. Meaning at some point, Ceres likely had underground briny liquid. It could have been pushed upward through cracks or impacts, then evaporated, leaving salt behind. That single idea pulled Ceres out of the dead rock category. And Dawn didn't stop there. It also revealed towering mountains, collapse features, fracture networks, and relatively young geological terrain. All of that points to one uncomfortable conclusion: Ceres wasn't always static. It changed. And in a place like the asteroid belt, where there's no atmosphere, no tidal heating, and no obvious energy source, that's a big deal, because it implies internal evolution. So scientists began to rethink what Ceres actually is. Not just a rock, but a small world that once had internal structure, heat-driven evolution, and possibly active chemistry. And here's where things get really interesting. A body under 1,000 kilometers wide, with salts, possible past liquid water, and complex geology. In small body classification, that's not normal anymore. It starts to look less like debris and more like a failed planet that never fully finished forming. And maybe, just maybe, that forces us to rethink what we even mean by small. As Dawn kept tightening its view of Ceres, something subtle started to bother scientists. At first glance, it looked like just another cold, dead rock drifting between Mars and Jupiter. Simple, quiet, predictable. But the closer they looked, the more it stopped behaving like a single solid object. It began to look layered. And that's when things got interesting. As the saying goes, the devil is in the details, and here, the details pointed inward. Using gravity measurements, shape modeling, and orbital data, scientists started reverse engineering what might be inside. After NASA's Dawn mission data became widely available after 2015, a fairly consistent picture emerged. Ceres wasn't uniform. It likely had layers. A mixed ice rock crust on the outside, a deeper, more ice-rich transition zone, and below that, a denser rocky core. So far, so standard. But the middle layer is where things get strange. Because it may not just be ice. It could be, or once could have been, a briny liquid layer. In other words, extremely salty underground water. This idea gained strength around 2016, when Dawn's observations of the bright deposits in a crater didn't just look like surface features anymore. They seemed chemically connected to what lay beneath. In simple terms, the salts didn't look like they arrived from outside. They looked like they came from within. And that leads to a much bigger hypothesis. Early in its history, Ceres may have had a subsurface ocean. Not a puddle. Not pockets of melt. An actual global-scale ocean hidden underground. Roughly 4.5 to 4 billion years ago, when the solar system was still young, Ceres had enough internal heat to make that possible. But here's the key point: that heat didn't come from the sun. Out there in the asteroid belt, sunlight is weak, almost decorative. The real energy came from radioactive decay, especially short-lived isotopes like aluminum-26 and iron-60. Early solar system material was basically a built-in heater system. That heat changed everything. Ice melted, materials separated, water collected, and a hidden ocean formed. But nothing like this lasts forever. As radioactive elements decayed, the heat faded. Ceres cooled. And the ocean began to freeze. But it didn't freeze cleanly, because salt changes the rules. As the saying goes, salt changes everything it touches. Salt lowers the freezing point, meaning the ocean didn't turn into pure ice. It became a messy mixture: ice plus trapped brine, a residual salty system frozen in stages. And that's why some models still suggest something surprising today. Ceres may still contain pockets of liquid brine deep underground. Not an ocean. Not a lake. More like a hidden, slow, salty plumbing system that may still shift in places. Then came another twist. Around 2017, analysis from Dawn's data hinted at organic compounds in some relatively young surface regions. Follow-up studies, including NASA reports and peer-reviewed planetary science papers, suggested something important: these organics might not have been delivered from space. They could have formed inside Ceres itself. Now combine three ingredients: liquid water or brine, organic molecules, and a salty environment. On Earth, that combination is familiar. It's the kind of chemistry that sits right on the edge of prebiotic processes. Not life. Not even close. But enough to make scientists pause. Because it suggests something uncomfortable: a world less than 1,000 kilometers wide may have once had the basic chemical toolkit associated with the origin of life. And that raises a much bigger implication. If Ceres could do this, what does that say about the early solar system? Maybe these environments weren't rare. Maybe they were common. And suddenly the real question shifts. Have we been misunderstanding small bodies all along? In the traditional picture, small objects are simple, cold, dead, static rubble. But Ceres tells a different story: internal layering, thermal history, evidence of past liquid water, chemical activity, and possibly lingering brine systems. It doesn't behave like debris. It behaves more like a partially built world that never finished forming. Or, as one might say, half-made but not half-dead. Still, there's no full agreement. Even today, key questions remain open. The bright deposits, are they from subsurface brine? Impact exposure? Short-lived activity? No single model fully wins. And the same goes for the interior. Some models allow liquid pockets today, others say everything is frozen solid with only salt residues left behind. The problem is simple: we've never drilled into it. We only infer. And that leads to the deepest question of all: why is something so small so complicated? Because most asteroid belt objects are exactly what you'd expect: dry, cold, geologically dead rocks. But Ceres behaves differently. It feels like a half-finished planet that accidentally got paused mid-formation. And here's the paradox: small doesn't always mean simple. Sometimes it means better preserved history. Because unlike larger planets, it never fully reset itself. So Ceres sits in an awkward middle ground: not dead, not alive, not fully anything. And that's what makes it so unsettling. It forces a bigger realization: maybe our categories aren't describing reality, they're just describing convenience. Placed back into the broader solar system story, Ceres stops being an oddball. It becomes a signal. A hint that small bodies aren't just fragments. They may be failed worlds, frozen worlds, or slowly evolving ones still changing in the dark. And that leads to an uncomfortable final thought. If Ceres is this complex, what else are we underestimating? Maybe the next redefinition won't be about Pluto. Maybe it will be about everything we thought we already understood. We don't have the answer yet. Not even close. Because we've never truly entered these worlds. We're still watching from far away, seeing faint reflections in the dark. Or maybe, just maybe, we're only now realizing something simple. The universe isn't quiet at all. We just weren't listening closely enough. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.